So welcome everyone to the third day of the camp, Conference on Applications of Polynomials. So our first speaker for the day is Michael Wheeler from Melbourne, and he'll be talking about LLT polynomials and their expansion over the modified Hall Littlewood basis. Over to you, Michael.
Okay, thanks very much, Alvin, for the introduction, and thank you very much to the organizers as well for the invitation to speak here. And I'd also like to thank yesterday's speaker, Misu Yu, who actually laid the foundation for quite a lot of what I'm going to speak about. So that means that I can at least skip some of those details. Okay, so yes, I'll be talking about LLT polynomials. And in particular, I will be saying something about their connection with certain families of integrable vertex models and some of the applications of that representation of the polynomials. And the main result is an explicit formula for the expansion coefficients over the modified Hall Littlewood basis. Okay, so I'll start by formulating the problem I'm interested in, but I'll try to do it with as little technical to define the polynomials in their full technical generality, because we kind of saw this already yesterday. So I'll just focus on the statement of the problem and also some of the reductions of the LLT polynomials. So LLT polynomials introduced in 1995 by Lascaux, Leclerc, and Thibon, and they're certainly a remarkable family of symmetric polynomials. They originally called them ribbon symmetric functions, and that was because they defined them in terms of a generalization of tableau that they call ribbon tableau. And so these days, this is referred to as LLT polynomials. And one motivation for introducing these polynomials is if you're interested in studying the Fock representation of this quantized affine algebra. So there is a Fock representation of UT of SLN plus 1, which is due to Hayashi. And basically in that representation, you take Young diagrams and you add boxes to the Young diagram, and the action of boxes corresponds with the action of the generators of the quantized affine algebra. And then there is something called boson-fermion correspondence, which will map the Young diagram polynomials. And so if you look at what happens to these Young diagrams under this mapping, effectively the polynomials that you get out of this are the LLT polynomials. So in some sense, they play the role of highest weight vectors in this Fock module. Okay, so this was actually something that LLT already spoke about in their original paper, but the presentation that they gave there for the LLT polynomials is not the one that I'm going to talk about. So indeed, I'm going to talk about the Bylan-Heyman version of LLT polynomials, where you have a polynomial which is indexed by vectors of skew shapes. So I'm going to have n tuples of skew shapes that will index my object. So this is going to denote an LLT polynomial indexed by two vectors of partitions, lambda and mu, and these are always going to be n-dimensional vectors. And you need that these vectors satisfy some containment constraints. So we always want that lambda I contains mu I for all I from 1 up to n. And so I'll just assume this without any further comment in the rest of the talk. Okay. So actually explicit formula for LLT polynomials. I'm not going to give it now. I'm instead going to talk about some of the reductions of LLT polynomials that are of interest. So perhaps the simplest one of all is when the vectors that you're looking at actually just become one-dimensional. So if you set n equal to 1, then LLT polynomials essentially reduce to skew-short polynomials. So the precise statement is that this L reduces to S of lambda 1 over mu1. Okay, when I just have one-dimensional vectors. So this is the SL2 case, if you like, of the theory. And there's another very nice reduction, which is when you set t equal to 1. And in that case, there is a factorization that occurs. So the LLT polynomial, when t is equal to 1, it actually factorizes completely, and you get just a product of Skew-Shor polynomials. And the indexing of the Skew-Shor polynomials, they're just the individual terms in your vectors. So, you know, lambda 1 over mu1, lambda 2 over mu2, etc., etc. So this is some sort of decoupling effect that happens when t is equal to 1. And in a sense, you could think of this as the classical limit of these polynomials where t is like a quantum parameter. Okay. And there's one further reduction, which I think was also mentioned yesterday, again, and that is that LLT polynomials have a certain stability property. So let's say a little bit about this. So in terms of the original formulation that made use of ribbon tableau, it says that they reduce to modified Hall Littlewood polynomials when the rank of the algebra n is greater than or equal to L, where L is the length of the indexing partition. So if you use a ribbon tableau version, the polynomials will be indexed by a single partition. So there'll be some big partition where the number of boxes in here should be divisible by n. Okay, because I want to put n ribbons on this thing now, so it has to be divisible by n. And if you look at that big partition, and if the length of this surpasses, or rather if rank surpasses the length of this thing, then in that case you reduce to modified Hall Littlewood polynomials. All right, so that's the statement that was originally given in LLT. But if you take this big partition here and perform this quotient map on it, so you basically split it into its n quotients, then you will get the statement of the result that's given here. So in terms of the formulation that we're using, this is essentially the version of this statement. So I'll take two n vectors of single row diagrams. Okay, so lambda now is going to consist of just these single row diagrams. So they're just Young diagrams with a single row. So the first one will have length nu1, and then all the way up to nu n. And the thing that I skew it by, this is just all going to be equal to 0. So empty diagrams. So for this particular choice, where nu is equal to a partition, we find actually that the LLT polynomial becomes equal to this object here. And this is the modified Hall Littlewood polynomial. So again, I haven't actually defined what modified Hall Littlewood polynomial is. We'll see an explicit formula for it later on in the talk as well. So if you like, those explicit formulas could be taken as the definition. But for this modified Hall Littlewood polynomial, Q nu of x xt, this can be viewed as an ordinary Hall Littlewood polynomial, where I perform a plethystic substitution. So I basically replace the power sum pk by pk divided by 1 minus t to the k. So this is quite a standard object, and this thing here is just the usual Hall Littlewood polynomial or McDonald's spherical function, depending on what terminology you like to use. Okay. So the goal of the talk, so what I want to get to at the end is to talk about the expansion of a generic LLT polynomial. So an LLT polynomial that does not assume this particular choice of diagrams, but for generic vectors of diagrams, I want to work out the Hall Littlewood expansion or the modified Hall Littlewood expansion for a generic LLT. And so in a sense, what this does is, you know, extend this stability result. So this result here is telling you that for a very particular choice, you get down to a single modified Hall Littlewood polynomial, but we sort of want to perturb now away from this and look at the case where you do not have the stability property. Okay. So here's the main result, or at least the first time that we will see it. So again, I'm not going to state it in the specific version now. I'll just give you a snapshot of the result. So we fix two n vectors of partitions, lambda and mu, and we'll define coefficients now that are indexed by effectively 3 partitions. So I have the 2 vectors here, and then I have a third partition nu. And these coefficients, by general theoretical considerations, these will be polynomials in T with integer coefficients. So that's really the first important thing to say here. These are actually not going to be positive in general. So in spite of the fact that they're not positive, they do have, in a sense, a combinatorial formula. Okay, so we define them as the expansion coefficients. I take an LLT polynomial and I expand over the modified Hall Littlewood basis. Okay, so here's the snapshot of the result. So basically, we're going to have a vertex model, which I'll give later. And that vertex model now, we're going to consider it on this square grid. And all of the information about these partitions now is encoded as the boundary conditions of that partition function. So effectively, what we will have is a way of encoding all of our partitions. So we'll have the mu partition will basically encode the boundary conditions at the bottom. The lambda will encode the boundary conditions at the top, and then nu will encode the boundary conditions along here. And this boundary will be trivial somehow. So the explicit vertex model, and we'll construct this partition function. And when you evaluate that partition function, you get this coefficient.
Sorry, may I ask a question?
Yes.
So is it possible to say what are the nu showing up on the right-hand side?
This nu here. Yeah, so it's a partition.
Yeah, but what are the non-trivial terms on the right? So what are the possible nus which occur in the right-hand side?
Oh, so you would like to know in general what nus you will get?
Well, maybe some condition, or I don't know.
I mean, the only condition is, I mean, you have that if you take the weight of the lambdas minus the weight of the mu's, then this should be equal to the weight of nu. But that's really the only condition a priori that you have. Yeah.
Thank you.
Yeah, and this basically holds because everything here is homogeneous. So, okay, so that's where I'm going to get to at the end. But before I give the specifics of this formula, I want to talk about some of the implications of the formula. So what you can actually do with it. Okay, so I'll go through a couple of examples. I think about 4 examples. So the first one is going to be the Littlewood-Richardson coefficients. Okay, so Littlewood-Richardson coefficients, very important in representation theory and Schubert calculus. And one way of defining them is if I take 2 irreducible polynomial representations of GLN, let's denote them by phi mu and phi nu. So these representations are indexed by partitions. And if I tensor those 2 representations together and then decompose irreducible, then the multiplicities that you get here are precisely the Littlewood-Richardson coefficients. So this is one representation theoretic way of defining them. There is an analogous definition that makes use of the Grassmannian. So if you prefer to work in terms of Schubert calculus, you can come up with an analogous definition. And more concretely, you can actually turn this into a statement about the Schur polynomials. So if I actually take the character of these representations, as is well known, these are nothing but the Schur polynomials in capital N variables. And so in that case, this statement here becomes just the multiplication rule for 2 Schur polynomials. So I take S mu times S nu and expand over the Schur basis, and then these coefficients here are precisely the Littlewood-Richardson coefficients. Okay, so that's one way of phrasing the problem. But there is another way of phrasing the problem, which is in terms of the skew-Shor polynomials. So there is an equivalent formulation of Littlewood-Richardson coefficients that says if I take a skew-Shor polynomial indexed by lambda and mu, and I again expand over the Shor basis, then I get, again, the same coefficients. And this basically boils down to the fact that the Shor polynomials are self-dual. So there is an inner product on the ring of symmetric functions, which is defined in chapter 1 of MacDonald's book, where effectively he looks at the inner product between two power sums. And up to a constant, I think I should call this thing Z lambda, or maybe 1 Z lambda, I can never remember. These two things are basically going to be, well, the two partitions have to be the same. Okay, so this is the orthogonality statement. And then if you apply this to the Shor polynomials, you end up with the fact that the Shor polynomials are orthogonal with respect to that inner product. And it's basically this orthogonality that ends up leading to this equivalent formulation of the Littlewood-Richardson coefficients. Okay. So now we get the first proposition. So I'll list all of these examples as propositions, even though really there's nothing very deep going on. So if we take n equal to 1, so the vectors of partitions are going to become one-dimensional. And let's write the first one just as lambda and the second one as mu. Then those coefficients that we were looking at before, when t is equal to 0, they reduce precisely to the Richardson coefficients. Okay, so the proof of this is very straightforward. So I'm looking at a single LLT. And I'm going to put t equal to 0. So this LLT here, it's in the case n is equal to 1. So as we've already seen, this is in this case just a Shor polynomial. So S lambda over mu. And furthermore, I'm expanding that thing over the, let's move this across. I'm expanding that thing over the Hall Littlewood basis. So I have here d lambda mu nu. And here is modified Hall Littlewood. In this thing here, I'm actually setting t equal to 0. And this thing, when t is equal to 0, this just becomes the Shor polynomial. So you see that indeed what you're doing here is expanding skew-Shor polynomial over the Shor basis, which is precisely the Littlewood-Richardson coefficients. So that's really the first result. So what we're looking at here, these puzzles, if you like, or these coefficients, they reduce to the Littlewood-Richardson coefficients. So there's some sort of big generalization of the puzzles or the honeycombs that were studied by Knudsen, Tao, Woodward back in 2001. So you'll see at the end when we actually draw the kind of pictures that one gets out of this, that they have a strong resemblance to honeycombs. And I believe that there is a mapping that one can do to make this statement precise, although as of yet I have not done it. So anyhow, so basically it's a generalization to generic n and also generic t of this result. Okay. So the second example that I want to talk about is again very closely related to the talk yesterday, and that is the Shor expansion of LLT polynomials. So this is a major unsolved problem, and based on what we've done, I think there is some progress for this particular problem. So let's try to motivate what exactly is going on here. So the first thing that one can do is to define analogs of Littlewood-Richardson coefficients, where instead of multiplying or taking the tensor product of two representations, I take the tensor product of n representations. So let's index these by mu1 up to mu n. And I take this tensor product and I again decompose over irreducibles, and I get some coefficients here. Okay. And equivalently, if I want to phrase this thing in terms of Shor polynomials, what it says is I multiply little n short polynomials indexed by these Young diagrams, and I expand that thing over the Shor basis and with some coefficients. So this is some generalization of the Littlewood-Richardson coefficients. So based on this particular formula here, this led Leclerc and Thibon to define a T analog of these coefficients. So the observation is here I have a product of Shor polynomials. And as we have already seen, the LLT polynomials are some sort of T generalization of products of Shor polynomials. So that means that if I just replace this, this left-hand side by an LLT polynomial, then I can define some T analog of the coefficients here, which are going to be these things. Okay. So these coefficients, they were studied in this paper from '98 by Leclerc and Thibon, and one of the things they actually showed is that they are certain types of Kazhdan-Lusztig polynomials. Okay? And another thing that is particularly important about these coefficients is that they are actually polynomial in T, and they have positive integer coefficients. So that suggests that there should be some sort of combinatorial understanding of these coefficients.
Sorry, can I ask?
Yes.
And so you can also, if you have the sequence of partitions, if you put them, place them on the same plane, you get a skew shape, and then this coefficients are just again usual Littlewood-Richardson coefficients for that skew shape, right? Is it?
Yeah. I think that will be related to the next slide. What you're asking. So maybe let's look at the next slide and then see if it. Yeah.
Sorry, may I ask one more question about this formula?
Yes.
On the previous slide.
Yes.
So you said that there is this expansion of the LLT polynomials, and this C of T, they are non-negative. So the right-hand side, as you said, S lambda is the character of a GLN module. So I wonder if there is a representation whose character is given by the left-hand side, or some natural vector space, which is the module for GLN, such that the left-hand side, the LLT polynomial, gives it character.
Right. Yeah, I don't know the answer to that question, but yeah, I can certainly see the motivation for this. Yeah, I mean, maybe the closest answer I can give to this is going back to what I said at the start of the talk. So you have these highest weight vectors for these representations of the quantum group that you're looking at. And if you take the boson fermion correspondence, those vectors map to polynomials. And in the SL2 case, they map to Shor functions. In the SLN case, they map to this LLT. So yeah, I don't think that directly addresses your question, but yeah.
Thank you.
Okay. So this is the formula that I was alluding to in answer to Anton's question. So yeah, so you can consider analogs of these coefficients where I take now n vectors of skew shapes. So I take an arbitrary LLT polynomial and I look at the Shor expansion of this thing, and then you can define some coefficients. So I hope that was what you're asking. I'm not sure. Maybe
I didn't know what I'm asking.
Okay, yeah. All right, so these are going to be polynomials in T with some non-negative integer coefficients. And so this was actually proved in a paper by Granovsky and Heyman from 2007. But their proof was not constructive, as was discussed yesterday. So the proof did not yield any explicit combinatorial formula for those coefficients. So Okay, so let me try to say something about the progress that comes out of the work that we have done. So basically you have this formula here. So these are the coefficients that we would like to obtain a combinatorial formula for. And one can expand them in terms of the expansion coefficients that we have found. And the expansion coefficients there are nothing but the Koska-Fultz polynomials. So Koska-Fultz polynomials, several different ways of defining these. So I can take just an ordinary Schur polynomial and expand this over the Hall Littlewood basis. That's one way of defining them. There's another way where I take a modified Hall Littlewood polynomial and I perform the same, except now I expand over Schur polynomials. So this sum is over lambda and this one is over mu. Okay, so this is how you define Koska-Fultz polynomials, and basically using this formula here, which expands the modified Hall Littlewood into the Schur basis, you can see that if you use this in conjunction with the actual main theorem that we have, you just glue the two things together and you get some sort of formula. Okay, so the formula is not ideal in the sense that, you know, the left-hand side here, this is positive. This thing here is also positive, but this one can have negative coefficients. So it's not a positive expression, but it is some direct expression. Okay, so I'll return to this in a couple of slides actually and give another version of that formula. Okay, so let's now do the third example. And so this is the Hall Littlewood expansion of McDonald polynomials. So this is making—
Sorry, Michael, before you continue, maybe can I ask another question? So you've given a connection to a number of coefficients that are well known. So did you look at the generalized Koska polynomials? Because they also are essentially arising as a deformation by taking a product of a sequence of Schur functions, which is exactly what you do, but rather than expanding them again in terms of a Schur, you would sort of do a monomial type expansion. And so it looks like there should be a connection to those as well. I just wondered if you had looked at that.
So you actually mean Koska numbers, right?
No, I mean generalized Koska polynomials.
Yeah. Well, given that I don't know what you're talking about,
okay, all right, some other time then. That's all right. So obviously you did not look at that. I take that as your answer.
Okay. So, okay, I'll erase this. It's irrelevant. Okay. All right. So yeah, so this next thing I want to talk about, this is making use of the work that was done in their paper by Hagelin, Heyman, and Lohr from 2004, where they gave an explicit combinatorial formula for the modified McDonald polynomials. And probably good to speak about that here, given that this is a workshop on McDonald polynomials. So let me try and give some statement of the result. Again, we actually saw it from the talk yesterday. So I will fix a partition index. So this here I'm using mu as the index, and I'll also define a certain set here. So this set here, rib of nu, this is going to be a set of ribbon diagrams. So what do I mean by this? So basically a pair lambda mu is going to live inside of this set if it satisfies the following constraints. So I take two n vectors of partitions and I look at the skew shapes by subtracting them component wise. And basically I require that each component is a ribbon. And furthermore, the ith component should be a ribbon of size nu I. So that's the definition of my set. And then for any pair of vectors that live inside of this set, you can define a certain statistic, which I have defined by, or have denoted by this W here. So let me try to at least give an example of how you compute this statistic. So what you do is you take your ribbon shape that's given here, and you essentially do a little mapping of this thing. So I will replace each of my edges here by dots. Right, so I'm going to put a dot here and a dot here, and this is going to be empty. This is going to be a dot. So I have this sort of thing. This is just a mapping from the ribbon to its Maya diagram, essentially. And what you do then is you arrange those dots on a line. So maybe I'll have a different color. So I'll have dot. This is going to be empty, then 3 dots, and then 3 empty spaces. And you label each of the sites by some integers. So this is going to be, let's say, 0, 1, 2, 3, 4, 5, 6, 7, 8. And then what you do is you look for the positions. I think in this case, I have to look for the positions of the empty dots. So these ones here. And I basically add up all of those numbers. So in this case, adding them all together, I get 0 plus 1 plus 2 plus 6. And so in this case, I get 9. So that will be the W that I associate to this ribbon. And then I have to do that for every single ribbon in the tuple. So I add all of them together, and that's how I define this W here. So it's some very simple statistic that you associate to the ribbons. Okay, and then this is the theorem. The modified McDonald polynomial is given by the formula here. So,
can I ask a quick question? So this statistic seems to depend only on lambda and not on mu. Is that correct?
So this, I mean, the point is those two things, lambda and mu, are not independent, because there has to be a ribbon. So once I fix lambda here, in some sense, this fixes the mu.
Okay. Okay. Yeah. Thanks.
Okay. So here's the formula. So J nu, I can express that thing as a sum over LLT polynomials, and precisely I sum over all ribbon shapes that live inside of that set here, and I put this W as the exponent of Q. So modified McDonald polynomials, they have an extra parameter. So I have this Q now, which enters into the game.
Could these ribbons be broken?
Sorry, I didn't hear.
Could the ribbons be broken? Or is it?
No, they should be connected. Yeah.
Yes. Okay, thanks.
And also, the usual notation for modified McDonald polynomials is H tilde, right? So are these the integral forms?
Yeah, so I kind of have my own notation. So indeed I should use the H tilde for this.
Okay. So this is H tilde, right?
I think as well there is an inversion of T that needs to happen in this kind of form. And so I think that the version I'm giving here differs from the usual one up to an inversion of T, and possibly multiplication by T to the n u, something along these lines. But yeah.
Okay.
So that's why I didn't want to give it the usual symbol. Because, yeah. But indeed, the use of the J here comes from the fact that this is a platistic substitution of the integral form of a McDonald. So indeed, yes. All right. So that's the formula. So what we can do now is we can actually take this formula and combine it with the formula for expanding LLTs into Hall Littlewood's. And you put the two things together, and now you get a formula for expanding McDonald into Hall Littlewood. So that's the result here. Okay, so let's define some more coefficients. So there are coefficients in this talk, so I apologize for the zoo of coefficients. So these are going to be indexed by two partitions. row and new. And basically what I'm doing here is taking the modified McDonald polynomial and expanding over the modified Hall Littlewood basis with some coefficients here. If you prefer, the non-modified version of this result is where I work with the integral form of a McDonald polynomial. And I expand with the same coefficients, E rho nu, Qt, and then here I just have a usual Hall Littlewood polynomial. So that's the non-modified version of this result. The coefficients are exactly the same. All right. So that's the objects that we want to study. And as I said, if you combine the Hagelin-Heyman-Lohr expansion with the expansion that we have looked at, then you end up with an explicit formula for those expansion coefficients. And so I should point out that these coefficients were studied in a paper in 2017 by Mellet, but to my knowledge, this appears to be the first fully explicit formula, combinatorial formula for those coefficients. And so if anyone knows otherwise, then please feel free to correct me. But yeah, to my knowledge, this is really the first combinatorial formula for those coefficients.
Can I just correct? I didn't really study these coefficients. I mean, it's a sort of, you can think as a byproduct of the paper that there's some information about these coefficients, but not really, there's no really study of this coefficient.
Okay. Okay.
No.
Thanks for the clarification. All right. So let's do the final example before I get into more specifics about the Vertex model. All right. So this previous expansion that we looked at, so this was given the label star. So this is, well, effectively this expansion here. This thing has a reduction that will lead to the Koska-Fulks polynomials. So it's essentially a reduction. Well, actually, it has two different reductions to Koska-Fulks, but the one I'm going to talk about is where I take Q equal to T here, which effectively reduces this thing down to a short polynomial, or at least the substitution of a short polynomial. And if I do the same thing on this side, then I'll basically be looking at the expansion of Shor over the Hall Littlewood basis. And that gives you the Koska-Fulks polynomials. So you get a formula for them. So here I've defined them. This C here, this is a standard normalization factor that's defined in chapter 6 of McDonald's book. This is just an explicit product over boxes inside of the Young diagram. Should be something like Q to the arm of S, T to the leg of S plus 1. So that's the definition of this C. Possibly this plus 1 exponent belongs over here. I can never remember which way around, but yeah. Okay. So this is the thing we're looking at, and the Koska-Fulks polynomials they end up having explicit formulas. So basically, I end up with this formula here. Okay, it's just by application of putting together all of the results that we've come up with so far. And so if I take that thing and I combine it with the previous equation dagger, so let's just go back and look at dagger. So dagger was an expansion for these coefficients in terms of the ones that we've been studying, multiplied by the Koska-Fulks. So now if you put the Koska-Fulks into here, then you get a new formula, and that's this one. So I think this is quite an intriguing formula. Again, for these coefficients that are very topical. So it's purely in terms of those D coefficients, which is very nice. And it has the flavor of a Cauchy identity, actually, because you're summing over all partitions row, and it's the same partition showing up here and here, and there is some normalization factor, and that's very standard in Cauchy identities as well. So this is somehow very similar to a Cauchy identity. So I think it's quite a nice formula. And so in some sense, this formula provides a combinatorial formula for these expansion coefficients of LLTs into Shors, because everything here is fully explicit. All right. Okay, so now I'll move on to really what is the second part of the talk. If there are any questions at this point, then maybe people could ask.
And just to confirm, the expansion, these e coefficients, they are not positive, right? Or
they are not. Yeah, they are not. Yeah. Okay. So I want to say something about a class of vertex models that that we refer to as fermionic vertex models. So I don't know what the level of the audience is in terms of integrable or vertex models or lattice models. So I'll say just some fairly generic things. So fermionic vertex model is an assignment of a complex weight. So that's this W here, and it assigns that weight to tiles. So a tile will basically be something like this. So I have 4 states that live around the edges of the tile, A, B, C, and D. And here the important thing is that A, B, C, and D are binary strings. So they're going to be binary strings of length n, and this n here is the n that has been floating around in the rest of the talk. And the fact that these things are binary strings, so zeros and ones, is really what makes this fermionic. Okay, so the first property that you typically have for these types of models is that the weight is equal to 0 unless the sum of these 2 vectors here and here is equal to the sum of these 2 here. So we refer to this as a conservation property. So it essentially says that whatever comes in here and here has to leave via here and here. So there's some natural flow in this direction. And that means you can actually map the tiles to trajectories of lattice paths. So there's a little example that I wanted to do here. So maybe I'll try and do it. So here A is equal to 0, 1, 0. B is equal to 1, 1, 1. C is equal to 1, 1, 0. And D is equal to 0, 1. So what you do now is you draw lines that correspond with these numbers. So we'll do the first set of lines in red. So the red is going to correspond with the first component. And effectively what I do here is I draw a line that goes from here to here, because both of those are 1s, whereas the other 2 are 0s. And likewise, I'll do this one in orange. These are all 1s. So then I have an orange line that does this and another one that does this. And the last one, let's do it in green. So this is a 1, 0, 0, and this is a 1. So that means the green line goes straight across like that. So that's how you can actually map these, these tiles to some sort of pictures, some sort of lattice paths. Okay. So a simple kind of fermionic vertex model that you can consider is the 5-vertex model. So the 5-vertex model has the weights that are given here. So it's a special case of the one that we've just been looking at, where you set n equal to 1. So all of your vectors now are going to be just one-dimensional. And so around the edges of a tile, you have basically 0 or 1 at every single edge. And
sorry, may I ask a question?
Yes.
Could you please go to the previous slide?
Yes.
So I wonder about these orange lines. Why don't you have a horizontal orange line?
Yeah, so you can draw the orange lines. There is some freedom about how you do the drawing. So really, the only important information is the boundary conditions, right? The fact that I have these 4 orange dots. But after this, I can complete the picture however I want. So if you prefer, I could draw it like this. this would also be okay. Yeah. So it's really the internal part of this tile is just decorative. You can draw it however you want. Yeah.
Oh, I see.
And what happens if there are an odd number of ones?
An
That
odd
is
number.
possible, right? Because you are adding vectors, not individual coordinates.
Well, you should never have an odd number of ones because you have this this constraint here.
No, but that is so how so I interpret that coordinate wise instead. I thought you interpret them as a sum in.
That's correct, but you can have something like say this coordinate is equal to 1, this one could be equal to 0, but then that means that these two will have to either be 0, 1 or 1, 0.
So if you interpret coordinate wise, I understand. Okay, fine. Thanks.
All right, so 5-vertex model, we have these weights here. So I won't say too much about the form, but let's just actually draw the pictures. So I get 5 pictures, which look like this. So I'm going to draw my paths like this. And have this. And each one of those gets a weight, which in this case is just something very simple. This is going to be 1, this will be 1, this will have a weight of x, this will have a weight of 1, and this will have a weight of x. So that's the 5-vertex model. And it's sort of classical and statistical mechanics. It's really one of the simplest non-trivial integrable vertex models. And it's very nice because it has bijections to, for example, lozenge tilings, which people like to study. So, okay. Well, there is a higher rank generalization of the 5-vertex model, and really this model has not really appeared so much in the literature apart from very recently. And so this is the explicit form for the weights of that model. So again, I go back now to the n-dimensional case. So each of these states now is going to be an n-dimensional binary string, and that's the explicit form. Okay, so I won't go into the specifics of the formula, but what happens now is you have actually n overlapping 5-vertex models. Okay, so it's as if you take the 5-vertex model from the previous slide, so this thing here, and then I take another copy of the 5-vertex model, which I can do using, say, blue paths, and then another copy, which I can do using green paths, and I just superimpose these things. And when you superimpose them, it's clear that the number of tiles that you get is just going to be 5 to the n. So these models have actually a very large number of tiles. But they are related in the sense by this t parameter. So it couples the models together. And so there is this entanglement factor here, which basically makes things non-trivial. So if this was not here, then you would just decouple into independent 5-vertex models. And indeed, when t is equal to 1, the models completely decouple and you get independent 5-vertex models. So already this model here, it should start to have the same flavor as LLT polynomials, because we've already seen that in LLT polynomials, when you send t equal to 1, they just decouple into a product of short polynomials. All right, so this is again an integrable vertex model, so it does have a Yang-Baxter equation, and it's been studied very recently. So first appeared in the paper by Cortiel, Gitlin, Keating, and Meser from December 2020. And then essentially a month later, with Amol Agarwal and Alexei Borodin, we also put out our text where we're essentially looking at exactly the same model. So, and in that work, we actually said something about the representation theoretic origins of the weights. So actually where the weights come from in terms of fusion of the fundamental matrix for this particular algebra. Okay, so let's now actually pass to the polynomials. So in order to give the formula for the polynomials, we need to use this mapping between partitions and Maya diagrams. So I already alluded to this earlier. So if I have a partition, let's say lambda is equal to 4, 3, 1, 1, then I can associate to this a Maya diagram where I'm going to have lots of sites now, and I can put either a stone or an empty space at each of the sites. And the way that I do it corresponds with this partition. So I'll just do the mapping very quickly, and then I'll explain. So in this particular case, this is what you get. So the way the correspondence works is you look at the stones, and for each stone, you count the number of empty spaces underneath. So this has got 1 empty space underneath, so that corresponds with this 1 here. And likewise, this has got 1, so it corresponds with this 1. And then this guy has got 3, which corresponds with this 3, and this has got 4. 1, 2, 3, 4. So this is the mapping. So with that mapping now, you then use it in the 5 vertex model, and you end up with a formula for the skew polynomials. So this is the formula. So I'm going to use this model. So these weights, and every single row has a different x parameter. So this is x1, x2, up to xn. And at the bottom, I'll put the Maya diagram that corresponds with mu, and at the top, I'll put the Maya diagram that corresponds with lambda. And then if you compute that partition function, you get precisely the skew polynomial. Now this result, it's been stated here in the language of vertex models, but it's actually really a classical result, because what you have here is nothing but the non-intersecting lattice path formulation of short polynomials. So really the formula here really comes as no surprise. Okay, so what we do now is we take that formula and we just perform now the higher rank extension of it. So this is the higher rank extension. So what I do now is I'm going to have not just a single partition, but I'll have a vector of partitions. So lambda is going to be equal to lambda 1 up to lambda n. And to that, I associate now, basically, I'm going to have a collection of Maya diagrams. So let's say I'll have n of these. And all I do is I just superimpose them. So, I take, this is one Maya diagram here, but then I'll have a Maya diagram for each of those lambdas, and I just superimpose them all together. And if you do that, then each of the sites here will now be a binary of length little n. And so this is basically how the mapping works. And in that case, you get a formula for LLTs, which looks very similar. So I go from x1 up to xn. And here I have the Maya diagram corresponding to the vector mu. And here the Maya diagram corresponding to the vector lambda. And the model that is being used here is this model. So using these weights. And once you have this thing written down, you can actually take the configurations in your lattice model now and perform a mapping of each of those configurations to an n-tuple of semi-standard Young tableau. And that n-tuple has an associated t statistic that actually tells you how the Young diagrams interact with each other. And this is, again, something that we saw in the talk from yesterday. So that's actually how you can prove that this thing actually gives you the LLT polynomial. So how much longer do I have?
Maybe another 5 minutes.
Okay. Okay. Yeah.
Michael, can I ask a question?
Yes.
On the left and on the right, your sort of boundary conditions that you just have zeros?
Yeah, so I should have said that. So indeed, these are all zeros, just empty, nothing here.
And then, of course, from the vertex model point of view, it's very natural to put parameters also on the bottom and the top, sort of in inhomogeneities. Is that interesting? Do you get sort of, I guess, in a polynomial into alphabet? Is that an interesting function?
For these particular ones, you can't really do it. And the reason is the weights are actually homogeneous in X. So if I put now some horizontal parameters, as you suggest, they will just factor out as an overall product of Y's. So you will not get any non-trivial contribution for these things if you just include Y's. If you want to include the Y's, then you have to work with a slightly different version of the model where the weights are actually inhomogeneous. And then you can meaningfully include these parameters. But as stated here, you can't really do it. But I should point out that, so in that paper, we looked at inhomogeneous versions of LLTs and actually define essentially a factorial version of LLT polynomials, where those parameters indeed play a meaningful role. So yeah, you can do this, yes. Okay. All right, so I think in view of the time, maybe I will skip this slide. So this was just something about the vertex model formulation of the modified Maclaurin polynomials, that effectively just you take the Hagelin-Heyman-Lohr result and translate that into the lattice model. But I will not say anything about this. And also not say anything about this. I'll just go actually straight to the main result now. Okay, so just a reminder, we're interested in computing these coefficients here. And we can do it now by making use of a vertex model where you have these weights here. So I won't say anything about where these weights come from. But underneath this, there is effectively a vertex model that is based on this quantizer find Lie superalgebra. So I have SL2n now. And this 2 here, this SL2, is telling me that I have one species of particles which will be bosonic, and I have n species of particles which are going to be fermionic. There's going to be some combination of bosonic/fermionic particles in the model. And the weights now, they are as follows. So I have now the following. So capital A, B, C, and D, these are binary strings as before. And little a, B, C, and D, these are going to be non-negative integers. So this is the thing I'm looking at. And they have some explicit form for the weights. Okay. So now here is the theorem. So those coefficients are given by partition function in the previous model, where at the bottom here, I put the Meyer diagram corresponding to mu. Here, I put the Meyer diagram corresponding to lambda. And here I put, basically I choose this one to be n0 and all of the other ones to be 0, 0. And over here, I put m0, m1, m2, where these m sub i's, these are the part multiplicities for the partition nu. So I should put with zeros here. So let me write it explicitly. So I take my partition nu. Well, actually, I have to perform, yeah, this is too complicated, but I have to perform some complementation of the partition. And then I express it in the multiplicative form. So 0 to the m0, 1 to the m1, 2 to the m2, etc. And then I put those m's into this boundary here. So this is just an encoding of nu, or nu bar, if you like. And so that's the formula. So it's a very explicit partition function that you can actually compute with. And I wanted to finish the talk by actually showing some pictures of what you get when you actually put this thing on the computer and work out the coefficients. So this should convince you that it's really a combinatorial form. So in the case n is equal to 1, and in that case, the vectors will just be one-dimensional. Here, I take this one to be 2, 1. I take this to be 0, 0. In that case, LLT polynomial expands over this Hall Littlewood basis. Here is one Hall Littlewood polynomial. Here is another. And these are the expansion coefficients. So these honeycomb type pictures here. And the precise form of that partition function is just this weight here. So in this case, equal to minus t. So you see that you would expect naively, if you just plug this formula into the computer, work out the sum, you would expect to get a huge number of pictures like this. But that doesn't happen. You find that most of the pictures have a vanishing weight, and you're just left with really the bare residue, if you like, and this is what you get. And a couple more examples. So here, this is a two-dimensional one. So the red and the green lines, they represent these partitions here. So let's maybe have a look at this particular one. So here, the red lines will represent this partition 2, 1. So this is the Maya diagram for 2, 1 here, and then the green will represent the second. So this is the Maya diagram for 2, which corresponds with this. And then you can work out the Maya diagrams for these ones. And the blue lines here, these are the bosonic particles that I was talking about. And so these things here, this actually encodes the partition that you're expanding over. Okay. And yeah.
And so these bosonic particles, they somehow go to the left top rather than to the right top.
Yeah, so that's right. So the fermionic particles want to travel like this, and the bosonic particles want to travel like this. Yeah, which, if you're familiar with the type of pictures you get for honeycombs, this is precisely what happens. So okay, so I think that's everything I wanted to say. So I'm sorry it was a little bit rushed in the end, but anyhow, this is the formula, and you can have a look at the pictures. I think these pictures are very, very pretty. I remember the first time I put them on the computer and saw them, it was like an alien life form was trying to communicate or something. It really looks like, you know, they're drawn by aliens or something. So anyway, thanks very much for coming to the show.
Okay, let's thank Michael for a very nice talk. Maybe these are the crop circles that they keep talking about.
Yeah.
Okay, are there any more questions?
May I ask one?
Can I ask it? Oh. Go ahead.
Well, you skipped one slide about SL2 head. Can you give some details or say some words about that?
Right. So yeah. So my plan here was to talk about two different formulas for the modified Hall Littlewood polynomials. So there's a first formula for the modified Hall Littlewood where the underlying thing is really ut of SL1n. And you get some vertex model formula for them, and maybe I'll just sketch it on this one here. So effectively what happens is you have all of your particles, they're all different colors, and they all enter in this column here. And what happens is these represent the end parts of your partition, and then they will leave at the top in some positions. Let's say something like this. This coordinate here, this will be nu sub n, and then this first one here, this will be nu sub 1. So these are the parts of the partition along here. And these things, they have to evolve in some way. So this is the formula that you get for modified Hall Littlewood. Then there is a reduction of this, which is kind of miraculous, but it says if you take the picture now and just replace all of those colored lines by lines of the same color, then you get a colorblind version of the same partition function. And that colorblind version is actually related to the weights that you get for SL2 hat. So there is some reduction from this one here to the SL2 hat, and these are the weights that you get. And furthermore, the formula that you get here, so the lattice model that you get for these things here, this formula was already found by Kirillov in 98. So you get some combinatorial formula that is basically Kirillov's formula. Yeah, so I do not understand very well how this works, say from a representation theoretic point of view. But there is certainly some correspondence between the partition function that you get here and the one that you get here. And it's a kind of miracle, but you have this correspondence.
Thank you.
Can I ask, so as I understand, the 5-vertex model, it's very easy to convert your pictures to some kind of tableau, right? It's straightforward. You just read the diagram row by row, for instance, and you get a sequence of Young diagrams, and that's your tableau.
Yes.
But in this more generalized situation, is it still straightforward?
It's exactly the same procedure. You do it for each color separately, and you get in tableau.
But what is this windings? There's some new kind of tiles, right?
Oh, so I mentioned windings here on this. So the windings are what you get when you go to when you look at the actual modified McDonald polynomial. So if you want to introduce the Q parameter, then effectively you put this model on a cylinder, and then the paths, they will wind around now, this sort of thing. And every single time it winds, you get a Q fugacity. So
okay, so you can also think about periodic tableau.
Yeah, but usually periodic tableau are periodic in this direction. So no, it's not the usual periodic. So there are periodic tableau that you can define, where you have periodicity in that direction. But here it's really you wind in this direction. Yeah.
And so there is this this Zelinsky pictures that give you this Littlewood-Richardson coefficients, the C lambda mu.
Right.
And can you give that style description of your?
I think so, because my understanding is that formula is very closely related to honeycombs, actually. So I think that the mapping could certainly be done, but this is kind of combinatorial work, so it's really, one has to take the formula and then do some bijections and things, and this is not really my strong suit, so yeah, I haven't really tried.
Thanks. Thanks a lot.
Any other questions?
May I ask a question?
Yes, please.
So Michael, does it exist a version of your vertex model in which you have coupling of stochastic 5 vertices instead of the ones that you considered there?
So it does depend on what you mean by stochastic 5 vertex model. Right. Yeah, I think the answer to your question is yes. So it should exist, yes. So I think.
So they should. Sorry, yeah.
The stochastic 5 vertex model, I believe, is the model that you use to construct, say Grothendieck polynomials.
Yes.
So it should be true that there is a higher rank extension of that. Certainly, yes. So I think it exists, but I'm not sure it was written down explicitly.
Okay, thanks.
Any other questions?
Can I ask a question?
Sure.
So the slide that you have right there, so your original paper gives a monomial expansion of the LLT polynomials. Is that right? My understanding correct there? So this formula there is a monomial expansion.
Yes, you can think of it as monomial.
So I'm just wondering. So is the symmetry somehow clear from?
Right.
I mean, from your Vertex model?
Yeah, that's a good question. So I didn't talk about it at all. So the symmetry is immediate from the Yang-Baxter equation. So there is a Yang-Baxter equation which I haven't spoken about at all, but that's basically where I take two of these tiles and I have a third object, which is the R matrix that intertwines. So this is an intertwiner for two representations. And pictorially, it looks like this. This kind of relation where the two tiles get switched around here. So if you apply this relation to the vertex model, you can basically come in and you can insert this intertwiner here. And you can insert it for free because of the fact that, so this comes back to Jules's question. So all of these, they're all empty here. So actually you're allowed to put this thing in for free because this is actually ends up being frozen for this particular choice. So you insert this intertwiner and then you use this equation and you can actually thread it all the way through here. This is called the railroad argument or unzipping argument, depending on who you talk to. And then it ultimately emerges from the other side. So it comes out here. And in the course of doing that, the two x variables, say, this is xi and this is xi plus 1, they actually get switched around. So from this, you get the symmetry immediately. Yeah.
Thanks.
Okay, if there are no more questions, let's thank Michael for a very nice talk. Okay, so I guess it's lunch break here in India. I guess you guys can, other places can have your tea break or whatever. And we'll meet at in about 45 minutes. See you all there.